Okay, welcome everybody. Today we have Micheline Soley, and you can all read the title. She will talk about experimentally realizable PT phase transitions in reflectionless quantum scattering. So when you're ready, go ahead, Micheline.
Thank you, and thank you so much for inviting me here to speak today. So I'm Micheline Soley, and I'm a theoretical chemist, and my expertise lies in near threshold systems and quantum scattering, especially in cold molecular systems. And so because of this, I was invited to collaborate with Carl Bender and with Doug Stone on looking at whether we could make experimentally realizable PT symmetric systems of upside down potentials that we could, for example, implement in cold atom systems. And so today I'll be talking about our approach to create experimentally realizable PT symmetric scattering systems. So this is the first example of a fundamental quantum scattering system where we can see PT symmetry transitions. And then I'll talk about methods that we've developed based on reflectionless scattering mode theory and WKB, or Wenzel-Kramer's Brillouin force analysis, both to show that this potential has the expected bound states for upside down PT symmetric potentials, as well as to give a physical understanding about why this works, why we're able to modify the potential based on ideas coming from quantum reflection. And then finally, I'll show that the new class of Hamiltonian systems that we're using in our approach allows us to not only see bound states of upside down PT symmetric potentials, but actually have experimentally measurable instances of PT symmetry transitions with measurable exceptional points. So the specific problem that was brought to me was the interesting case of weakly so-called bound states in PT symmetric upside down potentials, such as the potential -x⁴. And so this is a very interesting system put forth by Carl Bender in the late 90s, where here we have a potential that's upside down and goes to -infinity on both sides. And so one might think that since this is an upside down potential with unbounded energy, that if we place a classical particle on top of this potential, that the particle on top would be unstable. And so we might expect that there are no bound states for the system. But in fact, we can see that for a quantum particle, there are actually an infinite set of real energy eigenstates in these potential. And they're quite interesting eigenstates themselves because they're not true bound states in the original sense of the word, because typically when we're thinking about bound states, we think about potentials that are going to infinity, positive infinity on either side. So the wave function decays exponentially as x goes to infinity or -infinity. And so here we would expect a different kind of fall off. And similarly, the particle is going faster and faster as we get farther from the origin. So this kind of potential never supports plane waves that would be expected if the potential eventually levels out. So here also these kind of weakly bound states aren't true reflectionless states in the usual sense of the word either, because we can't come in with, say, a plane wave from the left and then measure the degree of reflection back. So this is a quite interesting, unexpected case of weakly bound states in PT symmetric upside down potentials. And in fact, this kind of behavior, it's not limited just to the potential -x⁴. So for example, it's also been seen in the potentials -x⁶ and -x⁸. And again, this is quite interesting behavior because these potentials with higher order, they're not just upside down. So it's not just that they looks, again, unstable with a particle on top, but they're actually decreasing even more quickly than the -x⁴ potential. So one might think of them as being, in a way, even more unstable than the -x⁴ potential. But yet again, we see that these potentials actually support an infinite set of real eigenenergies. And this behavior, in addition to having been seen in these upside down potentials, has also been seen in complex potentials that are determined by analytic continuation. So for example, here we have a Hamiltonian p squared plus x squared to the times ix to the epsilon, and in an alternative analytic continuation, which instead uses a potential x to the 4 times ix to the epsilon. And so if we think about the left case, here we can start by thinking about the standard harmonic oscillator case, which is known to have standard real energy bound states, which is at epsilon equals 0. So if we look at different values of epsilon, we can see a transition from having no real eigenenergies to having one real eigenenergy. And here it looks, so just to be clear, this isn't a ladder of eigenenergy states. It's actually the energy coming closer and closer to this asymptote here. Then we can see a finite set of eigenenergies and then an infinite set of real eigenenergies as we change epsilon. And we can see similar kind of behavior here with the PT symmetry transitions, now starting with the right side up quartic potential with standard bound states and then transitioning to the different sets of real eigenenergies for different epsilon values. Again, from no real eigenenergies to a finite set to an infinite set. And so if we think about the different potentials that are shown in these analytic continuation images, most of the potentials are complex. So just to highlight here, the only instances that correspond to the kind of upside down PT symmetric potentials that I was mentioning before are here. There's the minus x to the 4 potential that I began with, and this is the minus x to the 6 potential. And in addition, we have the minus x squared potential here, which supports no real eigenenergy eigenstates. And so now this raises the question of, if we wanted to actually see this kind of behavior in an experimentally realizable fundamental quantum scattering system, we have an issue, because most of these potentials are complex and it's difficult to implement or not possible to implement a complex potential in a standard closed, for example, cold atom system for fundamental quantum scattering. So this raises the question of, it invites us to think, how can we create a version of this kind of potential system that we can experimentally realize? So basically, the issues that we need to address are the following difficulties in implementing these kind of potentials in experiment. So first, we have the issue that the potential, such as minus x to the 4, has infinite extent. So it goes to minus infinity in x and to plus infinity on the other side. So the actual length of the potential we need to implement is infinite. And this is a problem because, unfortunately, as much as we wish they were, our laboratories are not of infinite extent. So we need to create a finite version of this system. And likewise, in addition to having infinite extent, these potentials also have unbounded energies. So as I mentioned before, on either side, the potential goes to minus infinity, which is not something that we can implement, for example, in cold atom traps. And then, as I mentioned before, we also have the issue that except at specific finite choices of epsilon, these potentials are complex. So this precludes implementation in the kind of cold atom systems that I was talking about previously, where we don't have the kind of tunability of gain and loss that we'd have in the kind of optical systems where PT symmetry transitions have been seen before. So this gives us an idea of what kind of properties we want to see in a version of the system that we could implement in quantum scattering experiments. So what we need is a potential that has finite extent. So for example, a potential where there's only a fixed region in which we see the potential changing with position, and the potential being flat elsewhere, so outside of a finite region of length 2L. And then we also require that the potential is bounded energy. So now instead of going to minus infinity on both sides, the potential should be of a finite height or a fixed minimum energy V max. And then lastly, as I said before, we need a potential that is real so that can be implemented in the quantum scattering experiment. So what our approach has been is to use a distinct truncated version of the unbounded PT symmetric potential. So for example, I'm showing an example, the truncated version of the minus x to the 4 potential of our approach here. And previous to this work, there has been related work by Carl Bender and Maria Giovanna Gianfreda about ways to truncate the minus x to the 4 potential, but that used a different approach and had different results that required length-dependent waves for scattering. So this is a distinct approach that is now not length-dependent. It does not require length-dependent waves, so it's a fundamental quantum scattering system. So the basic way that this truncated potential works is that here, the potential takes the form of the minus x to the 4 potential in the interior region. And then we smoothly connect it to being a constant potential outside of that region, with the hope that I'll show later is true, that by capturing the interior region of the potential, we can capture the basic physics of the eigenstates. And the way that we do this in practice is we use a potential that is minus x to the 4 in the interior region, so within distance L from the origin, and then it's minus L to the 4 outside of that region. And in order to make sure that this potential is smooth, we use a smoothing function to carefully connect those two regions together. So this is the choice of our smoothing function, and this ensures that derivatives are all well defined for the potential. So one might ask, now that we have the truncated potential, how does truncating the system make it differ from the infinite length version of the minus x to the 4 upside down PT symmetric potential? So as in the original potential, we have no bound states, because again, the potential doesn't go to positive infinity on either side. So we don't expect an exponential decay of the eigenstates in the asymptotic region. What is different though about this potential is now we no longer have the discrete set of real eigenenergies that we had in the original system, because we can support plane waves in the asymptotic region. So now this potential actually supports a continuous spectrum of states. So what actually maps to the original potential is that for this truncated potential, we have a discrete set of above barrier reflectionless states. So now the kind of states that we have are discrete are the states that, for example, come in on the left and leave through the right without reflecting back to the left. And just as a note, this kind of reflection behavior is purely quantum mechanical in character, since a classical particle that's, say, above a physical barrier goes straight through. This is the quantum behavior in which, if we're very close to threshold or very close to the top of a barrier, we can have a quantum reflection effect in which the particle reflects back from the direction it came. So here we have a discrete set of above barrier reflectionless states, both in the direction of going left to right, and then also right to left. So they're twin states. And so our hypothesis is that these reflectionless states will exhibit properties that are closely related to the reflection-free states of the infinite potential. And I'll show that this is true.
There's a question from Philip, if you
yes,
permit. Philip?
Please.
Yes. Good morning, Micheline.
Good morning.
If I were to lift up the potential so that where you've called minus 4,000, I call 0, then it looks like I've just got a potential step, except it's a little bit more smooth. So shouldn't I expect exactly the same quantum mechanics of scattering from this potential step?
Yeah, so that's a really interesting question. So you mean like basically a square barrier step?
Yes, a square, a bit of finite size.
Yeah, so I'll talk about you can show with quantum reflection analysis that you're going to see slightly different behavior for the step because a lot of the physics actually has to do with how quickly the potential is falling off. So basically, that kind of potential step is one limit of these kind of potentials. So
but are there new effects that you're going to show us that we don't get with the step?
Yes, there are new effects. You can actually, yes, yeah, by having this set of potentials minus x to the p instead of just the step, you can actually see that as a function of p, you can see PT symmetry transitions with totally real potential. So we'll see an interesting set of new behaviors.
Okay, thank you.
Yeah, thank you. And also just as a small caveat, so specifically for these minus absolute value of x to the p potentials, when we have an even integer value of the p parameter, the potential is analytic everywhere. But when we go to non-even integer cases and also non-integer cases, the potential is non-analytic, specifically at the origin. So the next question one might consider for the properties of this system is exactly how the symmetry works. Because if we think specifically about the potential, we can see that the potential is both parity and time symmetric. So where the actual PT symmetry comes into the system is not in the potential itself, but in how we impose the boundary conditions for finding the reflectionless states. So for example, here I'm showing the results for the P and T transitions for the right moving solution and the left moving solution. So for example, if we choose the right moving solution, we can define the boundary conditions at the edges of the truncated potential to ensure that the wave function is moving to the right. So then if we have time, if we use the time operator, we get the complex conjugate. And then if we use a parity transition, you'll see that we get the following, which if E is real, so if this quantity is real, then we get the same solution back. So we have unbroken PT symmetry, but we can also get a set of complex conjugate energies where we have broken PT symmetry. So basically, even though the real potential itself is both P and T symmetric, here the eigenproblem is PT symmetric only. So now that we have our, Philip, do you have another question?
Yes.
Yeah.
I'm sorry to ask so many questions.
No, please.
In standard non-relativistic quantum mechanics,
Yes.
if you have a symmetric potential, it has both symmetric and anti-symmetric eigenstates. Even or not. The eigenfunctions don't have to have the same, don't have to be even if the potential is.
Yes, yes.
So what have you done that's different than that?
So, sorry, so would you mind restating your question?
Yes, all I'm asking is, in an ordinary potential, a symmetric potential, V goes to V of x equals V of minus x. You can have solutions that are even in x and solutions, eigenfunctions that are odd in x.
Yes.
So it seems that your first step, that the right movers and the left movers are opposite, is one of the odd solutions. But it doesn't seem to be special to PT. Perhaps the PT is that the T then restores the symmetry. Maybe that's what you're looking at.
Yes, yeah. So here, so for the potential itself, it's P and T symmetric. For these kind of above barrier reflectionless states, so separate from thinking about, say, odd and even states of a harmonic oscillator, that's where you have PT symmetry only, is in the consideration of these above barrier reflectionless states. So does that answer your question?
Oh, all right. Okay.
Okay.
Proceed. Proceed.
Okay. So in short, what we have here is the first experimentally realizable fundamental quantum scattering system for seeing PT symmetry transitions. And it fulfills the requirements that I discussed before, because here the potential only changes within a finite extent of position space. Again, we have a bounded set of energies because we've chosen a maximum height for our energies, and the potential, the class of Hamiltonians minus absolute value x to the p is also completely real. So that means we can consider, for example, using cold atoms and traps to realize the potential and see these interesting states. So the question now that we have our framework of how we're going to represent the unbounded upside down, or how we're going to represent the upside down PT symmetric potentials, is how can we show that they actually have the predicted eigenvalues of the infinite system? So basically, how can we show that the truncated system is highly representative of our infinite length system of interest? And so in order to do that, we apply reflectionless scattering mode theory, which has previously only been, which is a general theory for scattering systems, but has previously only been demonstrated in optics. Here we adapt it and apply it to a quantum scattering to show that we have the expected eigenvalues. And then as well, to get a physical sense of why this truncation method works, we've also developed the Wenzel-Kramers-Berlin force analysis method that ties the behaviors to quantum reflection effects. In order to find the eigenvalues of the, in order to find the above barrier reflectionless states for our truncated potential, we employ a reflectionless scattering mode theory. So to give an idea of how this works in optics, the basic idea is consider that we have a scatterer and we're looking at what happens when a wave hits the scatterer. So in general, one would expect that if we have many channels that the wave can come in and leave through all of the different channels. So what relates to the system that we're discussing is a case in which we have reflectionless scattering. So here, instead of having both the wave coming in and out all of the channels, we can select certain channels where we want the wave to be incoming and other channels where the wave is going to be outgoing with no reflection back into the incoming channels. And this can be done due to properties of the scattering matrix, where we can consider a small reflection matrix within the scattering matrix that ensures that if we have input states in certain channels and none in the other, that we get output only in the remaining outgoing channels. And so essentially here what we're interested in is reflectionless scattering modes. So modes with real frequency that ensure there's no reflection back into the incoming channels. And such reflectionless scattering modes exist at any given frequency omega, as long as the determinant of this small reflection matrix at omega is 0. So in practice, the way one actually calculates these reflectionless scattering modes and reflection zeros, which are the analog that occur at non-real frequencies, is as follows. So let's say, for example, we have a photonic cavity, such as the one shown at the left. And let's say that we want the wave to only come in to these two channels and leave through the remaining channels. So there are two ways that one can find a solution. So one solution that's been done that we don't employ here is that one can match the wave in each of the channels to a plane wave coming in that channel through consideration of the scattering matrix. Alternatively, what we do is we impose fictitious, like purely for numerics, emitting and absorbing boundaries at the edges of the channels. So with those boundary conditions, one finds a spectra of our reflection zeros and reflectionless scattering modes as follows. So this is distinct from resonances, which, for example, they're shown with X's here, several of the resonances. So this is distinct from resonances that are typically used in quantum scattering calculations that represent purely outgoing states. Instead, now what we have here are special cases in which the wave is only coming in certain channels and leaving in the other channels, and with zero reflection occurring on real values of the frequency, such as this reflectionless scattering mode shown here. So this method is completely general and works both for classical and quantum mechanical scattering and in different dimensions, but has previously only been applied to optical systems. But we realize this technique is a great fit for our quantum scattering system because, again, here we're looking for reflectionless states where, say, we come in the left and there's no reflection back into the left with our one-dimensional potential. So what we've done is shown that reflectionless scattering mode theory also applies to quantum mechanics, which is somewhat interesting because the Maxwell operator equation of optics and the Schrödinger equation from that describes quantum scattering are not equivalent. So it's not trivial to see that the same kind of theories work in the two types of physical systems. But in fact, one can see that the derivation that shows that there's an infinite number of these reflectionless scattering modes in optics, so the derivation is done with temporal coupled mode theory, can actually also be shown in quantum scattering theory, now with quantum R matrix theory, originally from nuclear physics. And what this quantum application of reflectionless scattering mode theory has that optics doesn't have is related to the fact that it's often said that the equation of optics and quantum scattering are equivalent, but there's actually a small detail that makes quantum scattering have quantum reflection behavior that optics doesn't. And that's that in optics, if we look at the eigenvalue, it multiplies the permittivity, which is the analog of the potential energy surface in quantum mechanics. Whereas in quantum mechanics, here the eigenvalue does not is not multiplicative with respect to the potential. So here you have a different additive versus multiplicative behavior of the eigenvalue in the two different kinds of physical systems. And what this means in practice is that quantum mechanics has a unique above barrier reflection effect that's missing in optics, and that reflectionless scattering mode theory as applied to quantum mechanics includes and allows us to test our truncated potential.
If I may
We have another question.
If I may get another comment. The optics example that you've given is not derivable from a Lagrangian, whereas the quantum mechanical one is.
Thank you.
And
Yeah.
I don't know how significant that might be, but quantum mechanics explores the other paths that you get in the variational calculation.
Thank you. Yes, that's very interesting. Yeah, there's definitely a subtlety here that's often not included that has interesting physical effects, such as the one that I'll talk about today.
Yeah, I mean, I see the expression on the left in every textbook.
Yes.
But if you put epsilon of x into the Lagrangian, then when you vary, you'll get derivatives of epsilon of x in the equation of motion.
Yes.
And they're then ignored.
Yes.
So,
yeah. Yeah.
So it's very restricted. It's a very restricted problem.
Definitely. Thank you. Thanks for the comment. So we've applied reflectionless scattering mode theory, and we've seen that our hypothesis that the truncated potential accurately gives the eigenenergy spectrum of the infinite length potential is supported. So we see that with reflectionless scattering mode theory, as long as our potential surface has sufficiently long length, we can actually reproduce the low-lying energies of the infinite length potential with, say, 7 to 8 digits of accuracy. So here I'm showing results for the minus x to the 4, minus x to the 6, and minus x to the 8th potential that have all been calculated with reflectionless scattering mode theory. So we see that with shorter truncations, we accurately reproduce the lowest energy known analytically for the minus x to the 4 potential. And then as we increase our truncation length, we get more and more of the eigenenergies to higher accuracy. So here you can see close agreement for the first 6 eigenenergies of the minus x to the 4 potential. And then likewise, we can see the same behavior for the minus x to the 6th potential and the minus x to the 8th potential, where we see a very close agreement of the energies for the truncated potential compared to the infinite length potential. And so here I'm showing the lowest energies, and we can extend the agreement to arbitrarily high eigenenergies by increasing the length of our truncation. And we're currently looking into exactly what happens with the behavior of the spectra and whether what happens to the eigenenergies at truncated length. And so this confirms our ability to use a finite extent for the system. So the other thing that we needed to check is if it's also accurate to use a bounded energy. So again, we see with reflectionless scattering mode theory that with sufficiently large bound energy bounds, we again accurately determine the energies of the infinite length system with our experimentally realizable truncated system. So here you can see that with not as large energy bounds, we only get the lowest energies. And then as we increase it, we get the 3 lowest energies for the quartic, hexic, and octic upside down potentials. And here we can notice that the quartic potential is more sensitive to the bound in energy, which we can explain different ways. But for example, we can explain with quantum reflection in a kind of analysis that I'll discuss later. In addition to finding the eigenenergies of the infinite length system, we were very excited to see that the eigenfunctions themselves closely agree with behaviors that are expected for the infinite length system. So for example, here I'm showing the lowest energy eigenfunction of the truncated minus x to the 4 potential. And so it's been predicted for the infinite potential that as we go to larger x values, we expect to see a highly oscillatory function that's consistent with the fact that the potential is decreasing quite quickly. And here with an inset, we can see that as expected, the eigenfunction is highly oscillatory. And then so related to some of the ideas Philip was talking about, we would expect a symmetric probability density, which is also seen for the eigenfunction of the truncated potential. And then very excitingly, so I mentioned that for standard bound potentials, for standard bound states of right side up potentials, one expects the wave function to drop off exponentially with x. Whereas here with upside down PT symmetric potentials that are infinite extent, it's instead been shown that the wave function is expected to drop off as 1/x instead. And so we see that if we look at the height of the peaks of our eigenfunction for the truncated minus x to the 4 potential, we see with 3 digits that we reproduce the predicted 1/x asymptotic behavior. So we're able to get both the eigenenergies and properties of the eigenfunction that are expected for the upside down PT symmetric potentials, all with our experimentally realizable truncated system. And to further support that this system works, we also have quantum scattering calculations which reproduce the same behavior. So here we're using traditional quantum scattering methods to show the eigenfunctions for our truncated potential for the low-lying eigenenergies. And these traditional quantum scattering calculations are slightly more difficult to converge relative to the reflectionless scattering mode theory results, but again show that the energies are where we expect, both at the lowest eigenenergy, the first excited and the second excited state. So in total, this shows us that our truncated system works as expected in representing the infinite length system. So this gives us the question of, why does this work? Why can we actually use a truncated system to represent an infinite length system? And we have given a kind of physical explanation for why this happens based on quantum reflection. And so to give a quick idea of what quantum reflection is, the idea is that close to threshold at which some process becomes possible, one will see that quantum mechanics and classical results differ. So for example, if we think about this kind of tanh potential, very close to the threshold, the wave function the wavelength is very long with respect to the rate of change of the potential with position. And so what happens is that now you have disagreement between the quantum amplitude and predictions of the classical amplitude. And so as we increase the energy and get farther from threshold, we continue to have this quantum reflection effect, but at sufficiently large energies above threshold, now classical and quantum results for the amplitude will again agree if we don't have any kind of quantum interference effect. So with this idea that these quantum reflection effects can be used to explain processes having to do with above barrier reflection, we've developed a Wenzel-Kramers-Verleuen force analysis approach that allows us to sort of pinpoint where quantum reflection is happening in the potential, and whether it happens from the physical part of the potential that represents the upside down PT symmetric potential, or if it's erroneous and comes from the truncation itself. And so the basic idea of how this pinpointing technique works is focused in the difference between the behavior of quantum and classical particles. So for example, if we think about a classical particle in a barrierless potential, if there's no barrier in the potential, the classical particle goes straight through because there's nothing to stop it. And this is very different from quantum behavior that has the quantum reflection that I was talking about, where here, if you have a wave packet, and for example, a time-dependent quantum mechanics calculation, even if it's in a barrierless potential, if the energy is sufficiently close to threshold, you'll see the wave function actually reflect from a barrierless potential. So since we know that Philip, do you have a question?
Sorry again. Is what you've just said a violation of Ehrenfest's theorem or an alternative to it, perhaps? Because the center of the wave packet should follow the classical trajectory.
Yeah, it doesn't violate Ehrenfest's theorem, but it's a different kind of way of thinking about what's happening to a particle close to threshold. So it's not going against Ehrenfest's theorem, but a way to explain the reason for why we see quantum and classical amplitudes differing close to threshold. So you'd still see the same kind of behavior for the expectation value of the particle itself, but this is sort of a complementary effect to quantum interference, where we're understanding why the actual amplitude of the wave functions differ.
Well, maybe it's simply that Ehrenfest's theorem holds under certain conditions that are not holding here. Perhaps it holds for a Hermitian potential, but not automatically for a PT potential. And
this, just to be clear, this quantum reflection effect is actually universal and not just true for PT symmetric systems.
Okay.
Yeah, it's actually really interesting that this quantum reflection effect has been posited not just for, it's been posited for a wide range of physical systems. So it's been seen in like atomic and molecular systems as well in nuclear physics. So it's quite general, and it's really a consequence of the Schrödinger equation itself, rather than some kind of symmetry of the system.
Okay.
Okay. So now that we have the difference between the quantum and classical trajectories, we can consider the Wenzel-Kramers-Brillouin wave function, which is a semi-classical approximation that consists only of classical quantities. So, for example, if we look at the WKB wave function, it's made up of a classical density term and a classical action. And since we know that the classical particle can't reflect, anything that's built solely of classical particle information also has no quantum reflection. So we know that if the WKB wave function solves the Schrödinger equation for a specific potential, then at a given energy, then there's no quantum reflection for that system. And this is quite interesting because it means if we can find a potential close to our potential of interest for which the WKB wave function is a solution of the Schrödinger equation, that means the difference between our new potential and the original potential, which is the Wenzel-Kramers-Brillouin force potential, VWKB, actually shows us the source of quantum reflection for the particle at that particular energy. So what this looks like is if we have our Schrödinger equation here that's solved by the WKB wave function, we've derived that so it can be derived that the Wenzel-Kramers-Brillouin force potential takes this form. And one can, by relating this to distorted wave Born approximation, one can actually see that this gives us an understanding of where the quantum reflection comes from. So on the right is a sort of practical example of what this looks like for the minus x to the 4 potential. So if we take the original minus x to the 4 potential with no truncation, it's this red line here. If we include the Wenzel-Kramers-Brillouin forces, we get the effective potential shown with the dotted purple line. And the Wenzel-Kramers-Brillouin force potential itself is shown by the dashed orange line. And this tells us that the part of the potential that's responsible for quantum reflection is mostly concentrated in the interior region, which is far from our truncation. And so this gives us a kind of understanding of why we're able to truncate the potential. So if we calculate the Wenzel-Kramers-Brillouin force potential for different versions of our truncated potential for different values of the truncation parameter L, we get the picture that's shown at left. And what we see is that as the length of the truncation is increased, the quantum reflection causing areas that are due to the truncated potential, which are these sharp points here, become smaller and they move further out. And just to be clear, this kind of analysis needs to be calculated for each of the different eigenenergies separately. And this is showing an energy that's very close to the ground state energy. So basically what this is telling us is that as the truncation length increases, we get less anomalous quantum reflection effects caused by the truncated potential, and we get a result that's closer to the result for the infinite potential. So basically our hypothesis is supported that most of the kind of physics that we're interested in is in the interior region of the potential. And by having a sufficiently large truncation length, we can reproduce the known results. And this is also confirmed by a distorted wave Born approximation calculation of the reflection coefficients using the Wenzel-Kramers-Brillouin force analysis. And we see that with a truncation length that's sufficiently large, we see the low energy reflection behavior agrees with our expectation and converges.
Could I ask a quick question, do you think?
Sure, of course.
Okay, the sort of VWKB that you've got there.
Yes.
But if you actually if you started off with a potential with a harmonic piece and then also with the minus x to the 4th, that's quite a different theoretically from the problem with just the minus x to the 4th. So it seems to me that your kind of harmonic piece or something which looks a bit like a harmonic piece is very, you've got a formula in terms of V prime and things like that. So it's not arbitrary, it's very, very carefully chosen with respect to the potential that you have. This physics of this is different from if you have a physics of something like an x squared piece, even with a very small coefficient, and then minus x to the fourth. That's a completely different physical system from the one you have. Would you agree or not?
So the potential itself would definitely be different. The force analysis could also be applied in the same way. Here, the actual shape of the WKB force potential would definitely look different, because here you would be using a different potential, but it would still allow you to see what parts of this potential are responsible for quantum reflection. Basically, in general, what you'll see is that the WKB force potential is going to be largest where the change in the potential with respect to position is quite sudden. So for example, where you can see that it's quite small in this flatter region of the minus x to the 4 potential and sudden here. And actually, I'll show a little later, I'll show how this WKB force potential differs for different potentials, so specifically different p values for the minus absolute value of x to the p class of systems. And you can see qualitatively different changes in the behavior of the WKB force potential as a function of p. And it would be very interesting to also do this analysis for the minus x to the 4 potential with quadratic parts as well, to see how that would lead to different behaviors. So here we've seen that that the truncated version of our upside down PT symmetric potential accurately gives us the results for the low-lying energies of the infinite version of the potential. So what we were interested in is, we knew that our potential, it is non-analytic at the origin, but it's entirely real, so it's experimentally realizable. So we wondered, does that mean, could we use a class of systems of the same kind to actually see PT symmetry transitions as a function of p in that potential class v of x equals minus absolute value of x to the p, since these have only been seen in the complex analytic continuations that I was showing before. And we were very happy to see that, yes, in fact, we could use this novel class of Schrödinger quantum scattering systems to actually see experimentally realizable PT symmetry transitions. So in this slide here, I'm showing what happens to the reflectionless scattering mode spectra as a function of p. And you can see we get very similar to behavior to what I showed before, where we go from a region of p where there are no real eigenenergies. And then as we get to p equals 2, we have eigenenergies that are going to infinity and getting closer and closer to the line p equals 2, but never meeting it. And then we see a finite set of reflectionless scattering modes, and then an infinite set for sufficiently large p. And these reproduce the kind of behaviors that we've seen in the analytic continuations before, including the expected set of real eigenenergies for the minus x to the 4 potential, shown in the analytic continuation on the left, and our system on the right. And then also we also reproduce the fact that there are no real eigenenergies in the minus x squared potential and an infinite set minus x to the 6, in agreement with this analytic continuation shown here. And so this is related to Philip's question earlier. We see by using, actually, sorry, the next part will relate closer to Philip's question. But here what I'm showing is that quantum scattering results support and reproduce the behavior that we saw with reflectionless scattering mode theory, where we see a phase transition between having no real energy eigenvalues for the minus x to the squared potential to having a finite set as p goes to having a finite set, and then having an infinite set after p equals 4. So here we can see in the quantum scattering results for when we have minus absolute value x to the 1.2, we have no real eigenvalues, and then same at minus absolute value x squared. And then we see a transition to having our real energy eigenvalues. And as a reminder, these non-integer and non-even integer results haven't been investigated before. So actually, here's the response to Philip's question about what happens if we do WKB force potentials for other kinds of systems. So what we see is that by looking at the Wenzel-Kramers-Brillouin force potentials, we can also see that these transitions between having no real eigenenergies to having real eigenenergies are actually linked to quantum reflection behavior. So in this slide, I'm going to show a still of values of the potentials for different p values. And then in the next slide, I'll show a movie of what happens when you smoothly change p through different values for the different transitions. So here we can see that when p equals 1.2, so where there are no real energies or eigenenergies, the WKB force potential has a single peak right at the origin. And this corresponds to having no real eigenenergy with the analysis done again at approximately the energy of the lowest eigenvalue of the minus x to the 4 potential. So then we see a transition at p equals 2, where the peak becomes a smooth bump. And then as we continue increasing p, what we see is a formation of these two central peaks. So basically, you can see interesting transitions in the shape of the WKB force potentials that appear to be linked to the points of transition in the reflectionless scattering mode theory of the results showing PT symmetry transitions as a function of P.
May I ask a question here?
Please.
Go to the page before. Can you tell me from these graphs how many eigenstates you have?
That's a great question. So here, the calculation is, so the WKB force analysis has to be done at a fixed energy. It's basically telling you where the quantum reflection happens at what part in position space is responsible for quantum reflection at a given energy. And so this analysis is made at a fixed energy, which is it's approximately 1.477. So it can only give us information about that particular energy. So in short, from our current analysis, we haven't yet seen a way in which this particular fixed energy result can show us the total number of eigenenergies at a given value of P. But we could reproduce the same calculation at other eigenenergies to get an understanding of how the reflection behavior changes for higher energies of the higher eigenenergies of the different systems.
So in a sense, this potential is energy dependent and picks out one particular eigenstate.
Yes,
because
exactly.
usually if you have an effective potential, you can say, oh, this have an infinity of eigenstates and the other admits no eigenstates.
Yes, exactly. Yeah. So this is energy dependent and just gives you a picture of one energy eigenstate. And that's because of the fact that the WKB potential in general is only it only corresponds to one particular energy. So,
excuse me, but do how you make sure that it's not a superposition of several eigenstates of the system? So you excite the system with one specific energy, and this, in general, it can be a superposition of many eigenstates that exist in the system, and then eventually it support that signal that you are sending to the system.
Yes.
So you make sure that it is specifically the same eigenstate.
Yeah. So to be rigorous, the WKB force potential itself doesn't say anything about any specific eigenstate. Specifically, all it's telling us is about where quantum reflection effects are happening at a specific energy. So if one knows ahead of time that there's only one eigenstate there, one can think of it as representing physical effects having to do with that eigenstate. But if we think specifically about the physics, what it's really telling us is not about the eigenstate itself, but about how classical and quantum behaviors are differing at a specific energy. So if we have degenerate eigenstates, our analysis might be different there, for example. So it's a good question. So here I'm showing the same information, but now smoothly varying P to show the dramatic behavior in the transition. So here we have P at 1, which is a peak, a transition to at close to 3 to 2 peaks, and then the peak separating. And these different transitions appear to happen close to the PT symmetry transitions and point to some sort of link between quantum reflection behavior and the PT symmetry transitions we find in the experimentally realizable real potentials.
Yeah, but also here,
Yes.
if you start with this narrow peak at the beginning, in normal physics, you would say there's a delta potential where the poles would be in the complex plane. And if you go to a bound state delta potential, then the pole comes to the real axis. So when you are changing the shape somehow, the eigenstates, the poles, they move, the complex eigenenergies moves to the real axis, and suddenly they are here seen.
Yes.
Sometimes they're converging to complex eigenenergies.
Yes, yeah, exactly. So it would also be complementary to actually show the transition of the eigenenergies themselves during the transition between the complex eigenenergies and the real eigenenergies, which isn't shown here. So this just ties that community having to do with the complex eigenenergies to real eigenenergy transition to this kind of quantum reflection behavior that's often talked about in the cold atom community, where we're interested in experimentally realizing the system. So in addition to seeing the PT symmetry transitions, we also see exceptional points. And so here I'm pointing out the lower lying in P values of the exceptional points and a separate exceptional point here. And so this is exciting because when we had the analytic continuations that I showed before, those exceptional points didn't happen for real potentials. So it was unclear previously how we could actually see these exceptional points in a real potential in an experimentally realizable cold atom system. So by having these exceptional points here, we can now have a system where we could actually measure exceptional points in the laboratory. And so the following results are still in development. You'll see they have numerical noise, but we can basically see signatures of exceptional points at these two different P values. So for example, we would expect at an exceptional point that we get a transition between having a reflection ratio that looks linear to one that's more quadratic, which is seen for our results. And then we also expect a transition between a quadratic and quartic reflection coefficient, which is again seen at P equals 3.44. And then likewise, at the other exceptional point, we also are beginning to see that the scaled reflection coefficient again shows the expected transition that's a signature of an exceptional point. So in summary, now we have an approach that could serve as the first example of a fundamental quantum mechanical scattering system where we can have experimentally realizable and measurable PT symmetry transitions. And this includes measurable transitions between having 0 to finite and infinite numbers of real eigenvalues, and of course the transition between unbroken and broken PT symmetry, as well as the exceptional points that I was just mentioning. And outside of the PT symmetry community, this system is also interesting because previously the reflectionless scattering mode theory that I mentioned is quite general, has only been applied in optical system. And so the methods of reflectionless scattering mode theory, they're general for classical and quantum scattering and different numbers of channels and different dimensionality. But it has previously been used for optical systems such as photonic cavities, as well as free systems like scattering off of different objects. So what's totally new in this study is that here we have reflectionless scattering mode theory as applied to quantum systems. And this opens up a whole new world for applications of reflectionless scattering mode theory. So this is not a PT symmetric system, but a non-Hermitian system. And we have preliminary results that suggest that reflectionless scattering mode theory could be applied to optics, to quantum scattering for really interesting kind of control in actually chemical systems, because there's an analog that's to be made between reflectionless systems and 100% product formation in chemistry. So for example, in optics, we can have different waveguides coming into a photonic cavity and then leaving only through the other waveguides. We can actually make an analogy between this and chemical reactions, where there can be different channels that correspond to reactant channels and different channels that correspond to product channels. So since reflectionless scattering mode theory also applies to chemical reactions, it means that we can find sets of solutions where we can go from having all possible reactants to all possible products. And I didn't mention it because we were thinking specifically about our one-dimensional system, but in practice, it's been seen in applications for optics that in order to get this control, all we need is a coherent wave and two parameters, for example, being able to tune the width of these waveguide openings. So this is analogous to having in chemistry a coherent superposition state of our initial reactants, and then one or two controls that change the interaction between the molecules, for example, applied electric fields. So this points to reflectionless scattering mode theory not only being a way that we can see bound states of upside down PT symmetric potentials and PT symmetry transitions, but also having practical applications in quantum systems such as molecular collisions to direct ultra cold, extremely cold chemical reactions to specific outcomes. And in addition, reflectionless scattering mode theory, because of the way it's constructed, it's previously only been applied to finite light systems. So for example, Fabry-Perot cavities, finite scatterers, or finite size photonic cavities. Because we've seen that our truncated potential has similar behaviors to our infinite length potential, this points to the fact that finite length reflectionless scattering mode theory also has interesting applications in infinite length systems. In addition to this reflectionless scattering mode theory impact, it also has interesting impacts for Wenzel-Kramer's Brillouin force analysis methods. Because previously Wenzel-Kramer's Brillouin forces have only been used as numerical methods, for example, to calculate more accurately reflection above barrier through perturbation methods, and then also to change to increase the accuracy of complex absorbing potentials, which are akin to optical potentials or perfectly matching layers, and are used to study very cold or a variety of chemical systems. So here, the Wenzel-Kramer's Brillouin forces aren't just being used as these kind of numerical tricks, but actually giving us a physical understanding of the source of quantum reflection in physical systems. And in all this, this research that points to an experimentally realizable PT symmetry transition system gives us it invites us to look for PT symmetry transitions more broadly throughout quantum scattering, and invites us to look at other ways in which we can see PT symmetry related topics, for example, in cold atom systems. So with that, I'd like to thank Doug Stone and Carl Bender, as well as my funding sources, and you for your attention. Thank you.
And we thank you for your very nice talk. Thank you very much. More questions, comments?
Yes, I don't have a question. I just have to say to Micheline, I've got to run off to another meeting. I'm only up the road from you at UConn, so
Nice.
maybe we'll meet again at some point, but thank you very much for the talk.
Thank you. Take care.
Bye-bye.
Ami, you have a question. You're mute. You're
Yes,
mute.
yes.
Okay.
So I have a fundamental question. When we are talking about reflection, in principle, we assume that there's a wave or field which comes from one environment to the other, and then due to the interaction, it can pass or come back. But
Yes.
when we have this infinite potential, in principle, we don't have two environments, we have one, because
Yes.
it's infinite. So the wave always is in that medium. Unless you truncate it as you do it, you cannot talk about reflection.
Exactly.
There's a paradox over there. So you have infinite potential, so there's nothing to discuss about reflection. So when we say we have this reflection-less infinite potential, then conceptually I have difficult time to understand it. Because
Yes,
I
yeah,
need to come from another environment, but the potential is already goes to minus infinity, so I cannot enter from another place to this new environment.
Yes, yes, you have it exactly right. So in the infinite system, we can't really talk about reflectionless behavior because there's never, it's infinite in extent. You can't come in with a plane wave, say from the left, and see interaction with the interior region. So there, we're not considering reflectionless states. We're really considering what are those, quote, weakly bound states. That aren't really bound states and they aren't really reflectionless states. So the only place that we're really considering true reflectionless states is in the truncated system, where it's clear to see that you can come in with a plane wave. So what we're looking for is not the reflectionless states in the infinite length potential, but instead the relationship between the weakly bound states in the infinite length potential and the reflectionless states in the truncated potential.
Okay, then that's more clear. I have one more question. Is it okay I ask?
Yes.
There's no other question. The potential in principle, it has many states response, which now it is the reflection. And you are interested in the reflectionless solution, but obviously we have also solutions that they have reflections, and they physically they are also important, maybe for some other application. Now, my naive way of thinking is that these reflection potentials, they are easy to match the boundary condition and truncate the field somehow to have the same response. But the ones that they have reflection, they are the ones that they are difficult to achieve similar solution when you truncate them. Because over there, you need to play more with the boundary condition and transition going from one environment to the other one. I don't know if you guys thought about such type of solution, if you can match such type of solution for the infinite potential versus the truncated potential.
Yeah, that's a good point. Yeah, that's where the difference is, that in an infinite potential, you have a discrete set of eigenfunctions. Whereas in the truncated potential, now you have a continuous spectrum. So because now you can come in with a plane wave, and as you said, now there's not just the reflectionless states, but you can have, and generically in all other energies, you're going to have states with some reflection. So the real connection is between the reflectionless states of the truncated system and then the discrete eigenstates of the infinite length system.
Oh, okay.
Yeah.
Thank you.
Thank you.
More questions, comments?
If I may ask one.
Go ahead.
Yeah. So have you looked at the truncated pure parabolic barrier minus x squared?
Minus x squared, yes. Yeah, and we see that we see that there are no real eigenenergies for minus x squared. And we accurately reproduce that with reflectionless scattering mode theory for low-lying energies if L is sufficiently large. And we're actually looking at that in more detail about what exactly happens as you increase L. So in practice, when you increase L for that truncated minus x squared potential, you see accurately that there's no real eigenenergies for the low energies, but only up to some certain energy. And then we'll see that there are spurious eigenenergies again. So you basically have to keep increasing L in order to reproduce the accurate spectrum for within some energy range. And we're seeing right now exactly what happens to those real eigenenergies, why we see that behavior.
I see. Okay. So just one more thing. So how about the limiting case of sharp cutoff? Have you looked at that?
Yes.
I think you used a smoothing function. So how about if you take the limit of having a sharp cutoff instead of a smooth cutoff?
Yeah, so we briefly looked at what happens with the sharpness of the cutoff. Basically, you'll see that the quantum reflection effects increase that are due to the truncation itself increase as you make the sharper cutoff. And then there's also the question of where exactly you make the cutoff, because a sharp cutoff will matter more, like have more effects on quantum reflection if it happens at a not as low energy, because basically you want to make sure that there's no reflection from the area of truncation. Basically you want to make sure that the sharpness is not so sharp for any given energy that you're getting reflection from that transition. So basically, yes, we have looked at those, what happens in the limit of having an extremely sharp cutoff. And basically you will see some more quantum reflection effects from the truncation itself. So some higher degree of error from the truncation.
I see. Do you have this written down, and is it online already?
Not yet, so it's in preparation right now.
Okay, cool. Thanks.
Thank you.
More questions, comments? If not, then let's thank all Micheline once more for the really nice talk. Thank you very much.
Nice talk.
Thanks.